Okay, so if I'm going to show you where the lab is. I think I just sent you an email, so I don't think you even need to. I didn't even put it on here yet. So I put the lab in an email. It should look like this. I can't get to my Google Drive, but okay, so here's the lab. Let me show you, let me go to my diagram here and show you what we're going to do first. So we are going to take copper, aluminum, nickel, and we can have a like this. We know this is aluminum, so I think I've got some aluminum. What the heck? How did I manage? Where's my eraser on this? I don't even know. How did I end up with a pencil? I'll restart that. So we got some aluminum pellets, copper, other metals. We're going to take a 50 cc graduated cylinder. We'll take the bottoms off. Maybe this plastic isn't going to hurt to maybe leave on there. So we'll put some metal in there, and we're going to set this in boiling water. So if we set this in boiling water, and obviously if this water is boiling, water should boil at 100. This metal, which is going to be inside this graduated cylinder, should start out at 100. The idea is to find the specific heat of the metal. Okay, that's our whole goal. Then what we are going to do is we're going to use this container. Why don't I just restart this quick and maybe the lines will disappear. Yeah. Okay. So here is our calorimeter cup. So if I take this apart, if you look at it like this, there's an air layer in here kind of as insulation. So this is plastic. This really shouldn't absorb any heat. It's this inner cup here. We're going to have water in here. So we're going to know the exact mass of water. I think we put 100 grams of water in here maybe. Don't try to get the exact mass of water. Just pour in 100 milliliters because we've only got a limited number of balances. So I don't remember what it says. Maybe 100, 200 milliliters of water. I don't remember. But you're going to take water out of the tap. It's going to be about 20 degrees Celsius room temperature. This is sitting at about 20. Put your water in there, in this container, and then this will be your initial temperature, right around 20. So there's two things that are going to gain heat. We're going to dump the metal in the water. The metal's at 100, correct? The metal's at 100. It's going to get dumped into the water that's inside this container. The water is going to heat up in this container, and this metal container here is going to heat up. We are going to then have it set up like this. You're going to dump your metal in there, put the cap on right away. There's a rubber cork that goes in here, and this is a thermometer hole. It's actually a stirring hole, but we're not going to do it. We're going to swirl it by hand like this. This is actually for a stir, but we don't want to add that. We'll just swirl it like this. We'll use these. There's a temperature probe that'll go in that hole. It should tell us the digital temperature. And we're going to go for the highest temperature we get to. Okay? So we know the change in temperature of everything now. Right? We know the change in temperature of in everything. We know the metal's going to lose heat because it starts out at 100. The metal's going to lose heat. There's two things that are going to gain heat, and I'll show you all this in my calculations. I've got it all set for you. This aluminum container is going to gain heat, and the water in here is going to gain heat, right? And that should be equal. What is lost by that metal should equal the heat gained by this container and the water inside. So let's look at that in the lab right up. and it's right here. It looks like you're going to use 200 milliliters of water. That should be 200 grams, close to 200 grams. Pour that water inside this aluminum cup. That's what we're talking. So 200 grams of water. I'm probably not going to have, we'll probably use these Vernier ones. It's the same. All you're going to do is plug in. You get a digital temperature. So you're going to heat the metal for 10 minutes in boiling water. So it should be about 100. And you could stick your temperature probe in this if you want. Actually, we'll have 2 temperature probes. Just to be fancy, I'll bring 2 probes. If you want, you can stick it in the metal. It shows it here, but we're hoping that's going to stay that should be very close to 100. Now, in case I forget, when you dump the metal in, don't want any this is going to be sitting in water, the bottom of this, right? We don't want any of that hot water to dump as well. So we'll wrap the top of this with paper towels a little bit, plus that'll probably insulate. So when you dump it, any water that will come down will absorb into the paper towel and not get dumped in with the other water. Because we want just dry metal to get dumped in, right? So if we wrap a little paper towel around here, we'll be good. Okay, so then we'll dump that in there, and then here's the write-up. Here's a nice data table. Mass of water in the calorimeter. This should be close to 200 grams. It's 200 milliliters. Mass of your metal, whatever you get for grams. Mass of your cup. You can actually just put the cup on the balance. Initial temperature of your metal, this should be close to 100. Initial temperature of the water in the calorimeter, probably around room temperature, 19, 20. And the final temperature after you swirl it. Thank you, sir. Okay. So then there's just calculations here. The one that I attached, no, okay, yep, just calculations, and then there's some questions. But here's what it looks like. Let me go to my equations right here. Oh, hey, wait a minute now, get back here. Here. Yeah, they should be pretty close. Now, I don't know what I'm going to have copper, aluminum, lead. I'm going to have different metals. It'll be different metals. I'll probably give you, there's room for 4 trials. I might give you 2 metals and say two trials of 2 metals. So here's what this looks like. Let me go to this big equation. Right here it is. This should make sense. This is going to be the heat loss by the metal, Q metal, right? The water is going to gain that heat, and the calorimeter cup is going to gain that heat. So Q lost here by the water should equal Q gained by this. This Q lost by the metal is going to be mass of the metal, specific heat of the metal, change of temperature of the metal, right? And this change in temperature of the metal is going to be 100 minus whatever they end up at, T final. Because they're all going to be the same temperature at the end, correct? They're all going to be in thermal equilibrium at the end. Then you got your mass of water, specific heat of water, change of temperature of the water. This is going to go up. Your water is going to start at 20 or so. If you dump the metal in there, it's going to end up maybe at 21, 22. It's not much that it comes up. Then this, your mass of your cup, specific heat of your calorimeter cup, that's made out of aluminum, so we'll just use aluminum. And change in temperature of the calorimeter cup, which will change. This will be the same, the water in the cup. So if we're solving for specific heat of the metal, we'll divide the mass of the metal and change in temperature of the metal out. This should give us our specific heat of the metal, right? I did a lot of typing in this thing. It actually looks pretty good, I think. But that should work, right? Shouldn't be too bad. Question. Yep. Yes, this right here is going to be, yep, so let's go over this diagram. Yep, this diagram. Yep, there's going to be 200, inside this cup right here is going to be 200 milliliters of water, which will be about 200 grams of water. Yep, yep. And once we dump this metal, this 100-degree metal here, we're going to put a piece of paper towel around the top, right? We're going to dump this metal into this cup, and it's going to heat up the water inside the cup and the cup itself, right? And the cup itself. Yep. And then there's a sheet that you can fill in again, like this, and I've got this that'll calculate as well. So in my email, so your data, there's not much for data here, right? Masses of that stuff. And then the one that I posted, it's got some, up here it's got some specific heat values that you're trying to shoot for. Or the link I sent. So if I didn't, oh, the link, I sent that out in an email, didn't I? So that'll be updated. The new thing's in that link, so if you click on it, it'll show a different table. But we'll submit a spreadsheet again, and then I'll get you a new one. Okay, so that's the lab. Let's then look at, I got my supply list I got to pick up. We're going to look at, was it this question? Okay. Okay, so we'll look at that. So let's review what we did, because it's been a while. So this is what we looked at last time. If we were to calculate how much energy it would take to take ice at -40 and heat it to steam at about, looks like it might be at about 140. Looks like it's higher, but if we were to do that, it would involve 5 calculations. The amount of energy to heat the ice up, the amount of energy to melt the ice, the amount of energy, so let's start right here. This would give you 0-degree solid ice. This right here, by the time we get there, it melts at the same temperature. 0 degrees liquid water. We heat up the liquid water to 100 degrees. This is the amount of energy to boil it off, to get the steam at 100. To take your liquid 100-degree water to 100-degree gas or steam, then we'd have to heat the steam up. Notice it takes a hell of a lot of energy to boil water. It takes a lot. This whole flat line here, it takes what, 540 to boil the water away. It is a high heat of vaporization for water. You put water on a stove, even my gas stove, it's just cranking. You put a pot of water on a stove, it takes a while to boil. But and that's only this part of it. Yes, sir. Yep. 23? Okay. Perfect. Let's do this 21 first, and then 23 would be perfect. All right. We're going to melt 540 kilograms of copper. That's initially at 20. Oh, this is a great question. I should pay you after class. Okay. So we got a sample of copper. Cu for copper. A heavy metal would be lead, mercury, silver. So if you ask Alexa, you guys have Alexa, to tell you a science joke, she will tell you a science joke, and she'll say Mercury and lead walked into the bar, and the bartender said the heavy metal bar is down the street. That's an Alexa science joke. Her science jokes are pretty good. Her jokes are pretty good. So if you have an Alexa, just ask her to tell you a science joke or a joke. They're pretty good. Now, we have to take copper from 20 degrees Celsius. What temperature? We need to know what temperature it melts at. So we need to get our fancy chart out. And our fancy chart of this, well, first of all, let's get our specific heat. Our specific heat of copper is, let's use joules. 390 joules per kilogram degrees Celsius. That specific heat, 3.093. Now let me help you out with this too, because somebody asked it at 8 o'clock, and it's a good question. So here's your chart. And the question kind of is, this is calories per gram degree Celsius, correct? So if I take aluminum is 0.22 calories per gram degree Celsius. If I multiply this by 1,000 over 1,000, it would not change 0.22, correct? Because this is 1. Well, isn't there 1,000 calories in a kilocalorie? And isn't there 1,000 grams in a kilogram? That's why this is the exact same number. You can do it in calories, or it is 0.22 kilocalories per kilogram degrees Celsius. It would be the same number. So you can do calories or kilocalories per kilogram. Same thing. So for copper, for this question, it's 0.093 calories per gram degrees Celsius. We can decide later. Now, we need to get, if we're going to melt that, we need to get it to its melting point temperature. So we need to look at the other chart and say, what is the melting point of copper? And that melting point of copper is right here on this chart. Oh, shit. I didn't say that in the microphone. Shucks. So at this point, I don't see copper, right? That was, yeah, that's a good issue. That's a legit. So then you have to go to the trusty. Yeah, God darn it. This would be heat of fusion. This engineering toolbox has a lot of stuff in it. So we need the heat of fusion of copper as well. So it looks like 49, it doesn't matter. We'll use calories. 49 calories per gram. So that's heat of fusion. That's going to be the melted, because we have to melt it, right? So let me switch to this. What was the number? 49 calories per gram, right? There's calories per gram. Okay, then all we need now is the melting point. And usually we need periodic tables. It doesn't tell us the melting point, but I wonder if I got another table I need to. It looks like 1,085 here. Copper, 1,085. So we need to get up to 1,085 Celsius. So here we go. So here's what we need to do. There's going to be two calculations needed. We need to find out how much heat it takes to get from 20 to 1,085, and then just how much heat to melt it. So this Q total, I'm going to put Q total, is going to be the heat needed to go from 20 to 1,085 plus the heat needed to melt it. Because all we have to do is melt it. So what temperature is it going to melt at? 1,085. So this is going to be MC delta T plus M times the enthalpy of fusion. That should do it right there. And you can convert joules to, I'm not sure what the answer is in, but that should do you then. It's going to take those two. And then 23, what quantity of heat is needed to convert 2 kilograms of ice? Okay. So let's look at this. Let's look at our steps we need. Oh, this is, oh, I need to buy you a pop or something afterwards. 2 kilograms of ice. So, ice, we need to get from negative 25 to 0, correct? We got to get our ice from negative 25 to 0. So that is going to be MC delta T, where this is going to be the specific heat for ice, right? Okay. Number 2, we have to take ice at 0 degrees Celsius to water at 0 degrees Celsius. Ice at 0 to water at 0. That is going to be mass times the enthalpy of, think of water as fusing the molecules together. We use an F for fusion. And we're going to add, we'd have to add these up when we get all done, right? These are specific ones. I just want to make sure you get the steps here. Number 3, we got to get water at 0 degrees Celsius to water at 100 degrees Celsius. Because we got to get the steam at 100. So this is Q is equal to MC delta T. And this would be specific heat of just water this time, right? It's got to be specific heat of ice here, water here. We got to get water at 100 degrees Celsius to steam at 100 degrees Celsius. So we got to turn everything from a liquid to a gas, right? And this is going to be Q is equal to M times the enthalpy of vaporization, V. And we'd have to add those 4 up. Does that make sense? We'd add those 4 up. Is that all right? So there's four heat calculations, and then you're just going to add all 4 of them up. If I put a plus sign, plus sign, plus sign like this, we'd have a total. Okay, good question. Anything else? Questions? Okay, we going to just finish this up. We're not doing this whole thing. We're going to do two problems, and we're going to call it good here. This example here in the book, I have to clarify this baby, and we're going to do this example. So you have a nice plasticky styrofoam insulated cup that you add ice to it. So you have 3 ice cubes are used to chill a soda at 20. Now this would be room temperature. I'm cheating. Are we pop or soda? We're pop, right? What state were you? You buy pop and you drink soda? Now this blew my mind. You're from the South, what state? That's what blew my mind right there. I'm in Alabama. I'm in a restaurant in Alabama. The waiter comes over to our table, and there's like 6 of us there. And she says, quote, "What would you like to drink?" And my nephew says, "I'll have a Coke." And the waiter responds immediately, "What kind of Coke?" "Root beer."
Yes, that's how it is.
Everything is a Coke.
But then when you move up here,
Yep.
you refer to it as pop. You guys
Yep.
refer to your soda as pop.
Correct.
Well, you might not know it if you won't live here. It might just be normal.
But that Coke episode blew my mind in Alabama. What kind of Coke? 7-Up. Yeah. What kind of Coke? 7-Up or Dr. Pepper? Yeah. Blew my mind. I guess Coke. Yeah, what kind of Coke? You'd have to say regular Coke. Oh. I'm changing this to pop. I can't take it. Okay, now, here's what's going to happen. We have an insulated container and if this is insulated, we've got 0.25 kilograms of pop. Essentially, it has the same heat capacity as water, especially if it's diet, because there's no syrup. I mean, there's nothing to it for diet. So 0.25 kilograms. I've got 3 ice cubes that we're going to drop in here. Okay. So we got 3 ice cubes at 0. And those are 6 grams each. So that's only 18 grams. And if I put that in there's 3 ice cubes, 3 times 6, 18 grams. 0.018 kilograms of ice, right? Either one. Doesn't matter. Because we can always change the unit at the end. It started out in kilograms here, so... Yes. These are the same. So the specific heat of water, or let's use aluminum. It's 0.22 calories per gram degree Celsius, or 0.22 kilocalories per kilogram degree Celsius. It's the same. Kilograms, 2,000 grams. You mean 1,000 grams? 2,000 grams. Yeah, that's fine. Yep, that's fine. Yeah. Just so it doesn't matter what you use, just so that when you multiply a mass here, obviously you can't be doing 100 grams and then use this, because your grams and your kilograms aren't going to cancel, and use this number because then these aren't going to cancel out. Just so, it doesn't matter what you use as long as you make sure your units work. So we can do these grams, kilograms, we can do it in joules, whatever. We'll do this in kilograms since that's what I started. Now here's what's going to happen. It wants the final temperature when all the ice is melted. So what happens for this problem is this. As this starts to melt, you're also creating 18 grams of liquid water in the end as well, correct? You're going to have 18 grams of liquid water, and everything's just going to be a solution when you're done. So we have something like, looks like this. We're going to go Q lost equals Q gain, just like we always do. Now, what is going to lose heat? Yeah, what's going to lose heat? What's that? Well, no, this is going to be the ice, huh? Where the soda is going to go down. I'm sorry. What's going to gain heat is the ice. Then water. That's going to lose heat here is our pop. So our pop right here is going to be, we treat this as, especially if we have diet pop, it's pretty much as water. So we'll go mass, I'm going to write it out like this though, mass of my pop, specific heat of my pop, change in temperature of my pop is going to equal to the energy to melt plus my gain of my liquid water. Now I'm going to have water. Because as this starts to melt, it's going to go into the water. When we're all done, we're going to have 18 extra grams of water in there, correct? So this one's kind of goofy because not only are we melting the ice, and then we're going to add that much extra mass to the whole container to get the final temperature. So I'll write this out in one line now. Mass of pop, specific heat of pop, but let's do this. Remember, our temperature changes here have to be positive. That pop starts out at 20. Is it going to end up less than 20 or more than 20 if you put ice in it? It's going to be less, correct? So again, this is the key to making these just if you do this part correct, the rest of it is just crunching the numbers. So we want this to be a positive value inside here. We need to put T final in, so we're going to go 20 minus T final. Then we need to melt the ice. This is going to be my mass of ice. Enthalpy of V or F? Am I making a vapor or a solid? Am I talking a vapor or solid? Fusion. Ice. So that's going to be an F for fusion, right? Think of solids as you're fusing something. No temperature change, correct? No temperature change because you're just melting the ice. It's already at 0. Plus, you're going to get this extra mass of water, specific heat of water, and then the temperature change of the water. Now, this starts out, the liquid water starts out at what temperature? Once you melt it, it's at 0, right? It's at 0. So this is going to be T final minus 0. This is that ice cubes, once they all melt, they're going to raise up and be, everything's mixed together. So at this point, we just got to crank this out. So I am going to write this in, my mass of my pop. Am I going to, yeah, I'm going to write, this is going to be 0.25 kilograms. I'll do this in calories. So this is going to be, treat this as liquid water. What's the specific heat going to be if we do it in kilograms? 1 kilocalorie per kilogram degrees Celsius, right? Kilocalorie in kilograms then, instead of 1 calorie per gram? My mass of ice is 0.018 kilograms. My enthalpy of fusion for water, it's going to be the enthalpy of fusion for water is, I have this in kilocalories per 79.7. This is in kilocalories per kilogram. .018 kilograms. And then this will be 1 kilocalorie per kilogram degrees Celsius again. Let's clean this up and solve. No, I would never do that. You could if you kept track of it, but so this is going to be 0.25. So we're going to have on the left side 0.25 times 20 minus T final equals 1.4346 plus, this is just going to be 0.018 T final. Oops. All right, that doesn't look bad at all. This would be 1/4 of 20, which is going to be 5, huh? 1/4 of 20 is going to be 5 here. 0.25 times 20, we're going to have 5 minus 0.25 T final. So we are going to put this to the other side, make it negative, put this to the other side, make it positive, put my T finals on the right. Looks like that'd be the easiest. So we're going to have 5 minus 1.4346 equals 0.25 T final plus 0.018 T final. This is 3.5654, and this is 0.268 T final. 0.268, yeah. 3.5654 divided by 0.268. 13.3. once you got it set up, it's just cranking it out, right? So 13.3, that'll cool it down some. It's not very much ice. 6 grams. That's probably 3 small cubes, but it does a little. Then, this is going to be the last thing. We are just going to do a conduction calculation. We're not going to do a bunch of others, but it's an interesting equation. Q over T, think of it for conduction, molecular collisions. An example of that would be if this is a chunk of copper, put your, oh, be careful now, here comes a great drawing. Oops. Put your hand on the copper here, light a flame to it on this end. The heat's going to transfer or conduct to the other end, correct? Now, how fast it get there is going to depend upon the metal, right? But that is, you're going to speed up this, what we talked about before, these atoms of copper banging back and forth into each other. That's going to get transferred down the copper pipe until you let go of it, if you're smart. Now, this happened to the biology teacher's son. He has a fireplace at his house, and his son was only a year old, or a little over a year. And he crawled up there and he planted his hands on the glass on fire and never let go. So he'd have skin grafts at a 1.5 years old. Now, the code is there's supposed to be wire loops on there, so there's an air gap. Just be aware, if you have a glass fireplace that's an old one, that glass is straight hotter than heck and nobody knows it. So for a little kid to have skin grafts is, and you just see a kid crawling on there and just planting their hands on there and not letting go, right? Well, do they have enough balance to throw that? And they don't have enough balance to throw themselves back, right? I mean, their weight, if he crawled up there and, yeah, not good. So this is be transferred, this could be joules per second, it could be calories per second. It's just a rate. It could be watts. A watt is a joule per second. This K is the thermal conductivity of the material. Look at the unit. This unit for K is joules per second per meter per degree Celsius. A is the surface area. D is the thickness of the material. And this is the temperature change between the two sides. These K values down below then, we have K values for different metals. We'd have to look up a K value, and this makes sense. Materials with large Ks are good conductors. Small Ks would be insulators, right? So you're down at the bottom, you've got air, polyurethane, goose down, wool, cork, fiberglass, wood, human tissue. You got concrete, water, glass, ice, steel, and so on. So with the time left, we're just going to do one calculation. We're not. The other one has R values and things like that. If we're in if you're the HVAC class, I would go through more. But here's just one calculation we're going to do. You got a styrofoam ice box. Okay. The total area is 0.95 meters, so that's my A. The average thickness, 2.5 centimeters. This is 1 inch, right? 1 inch styrofoam, 0.025 meters. Inside the container, you have ice, you have water, canned beverages, Mountain Dew at 0 degrees Celsius. So you've already got them cold. The inside box is kept cold by melting the ice. Makes sense. One day if the ice box is kept in the trunk of a car at 35. So basically we're calculating how much ice are you going to melt. Do you have enough ice? They're assuming you have enough ice, otherwise we'd be in trouble. So my equation for this, I'm going to use the equation we just looked at, which is, and I'm going to multiply by T right away. So it's going to be this. All I did, this is the amount of heat, right? That's a K. But here's my problem. Since my K has seconds in it, I need my time to be in seconds. So let's solve that problem. Is it 1 day? Yeah, 1 day. Let's see, 24 times 3,600, 24 times 3,600, 86,400 seconds. Now, this problem should give us K, and it doesn't. K of styrofoam. That's my K. Should I be making my, is it a goofy looking K like that? There's a regular, it's a regular K. K for styrofoam is 0.010 joules per second per meter per degree Celsius. The styrofoam's not on our table for some reason. Is it the same as polyurethane? It should. No. No, polyurethane's going to be a hardened, more gooey plastic. So we're just going to plug, we've got everything to plug in here. We've got 86,400 seconds. Our K value is 0.010 joules second meter degrees Celsius. .950 square meters. The difference in temperatures inside and out are 35. It's 35. The distance of the wall is 0.025 meters. That's going to give me how much joules of heat is transferred into the container. That joules of heat that gets transferred in is rounded to this. $1,150,000 joules. That is going to go into the heat energy to melt the ice. We're looking for the mass of ice right here. This is my ice melting. So we're going to solve for this. This in joules is 333,000 joules per kilogram. So if we take that and divide it out, we're going to get 1150,000 divided by 3.45 kilograms. That's how much melts. So as long as you got at least that many kilograms, that's about, what, 7 pounds. As long as you got 7 pounds of ice in there, you're still good. Otherwise, not so good, huh? Notice I did Mountain Dew for the canned beverages. Okay, that is going to finish us up, and that's what we're done. Lab tomorrow.